In this problem, we're going to look at another titration. This particular titration, you obtain 20.0 milliliters of 0.180 molar potassium hydroxide. So that's what's going to be in your Erlenmeyer flask. And this time up in your burette, the titrant is going to be phosphoric acid, H3PO4. And to reach the endpoint, it required 14.0 milliliters of that acid. So we need a balanced molecular equation, because I know at some point I'm going to be using solution stoichiometry. I need my recipe, which will be the function of the molecular equation. So the potassium hydroxide and the phosphoric acid are both in solution. They're both ionic compounds. I know that even though this is a neutralization reaction, it is really a subcategory of a double replacement reaction. So the potassium will go over and join up with the phosphate. Potassium has an oxidation state of 1+, phosphate oxidation state of 3-, so the correct formula is K3PO4. The hydrogen will go hook up with the hydroxide. Hydrogen is 1+, hydroxide is 1-, so of course I get water, and it is a liquid. My skeleton equation, I notice, is not balanced, so I go after the potassiums first, and I put a 3 out in front of the potassium hydroxide. Then I looked at the hydrogens, and I saw that I had 6 on the left side, so to get 6 on the right side, I need 3 water molecules. So there's my recipe. There's a 3-to-1 ratio between the potassium hydroxide and the titrant phosphoric acid. Now we'll write out the net ionic equation for this neutralization reaction. And of course that involves the hydrogen ions and hydroxide ions joining up to form water. There were 3 hydrogens and 3 hydroxides to give me 3 water molecules. Since I have a common factor, I can divide through by 3, and I get my classical net ionic equation for neutralization reaction, hydrogen and hydroxide giving us water. Now I want to use my stoichiometry, and I'm going to try to find the molarity of that titrant. It was unknown at the beginning. Let's see if we can find it. This is solution stoichiometry, so I don't have the number of moles directly. I'm going to have to use my molarity equation because these are mixtures. So molarity, again, is number of moles of solute per liter of solution. I know more about the potassium hydroxide. I know 2 of those 3 things. So I'm going to use this equation using the potassium hydroxide. I know its molarity. I know what volume I had taken originally. And in that 20 milliliters, I know I have 0.00360 moles of potassium hydroxide. Relying on my recipe, my balanced chemical equation, I'm going to now calculate how many moles of phosphoric acid were required. I noticed that there was a 3-to-1 ratio. Phosphoric acid contains 3 hydrogen ions in it. I don't need as many moles, so the ratio is 1 to 3. I'm going to divide by 3, and it turns out we have only 0.00120 moles of phosphoric acid. So this is called a polyprotic acid. It's got more hydrogens per molecule than we might have had with a monoprotic acid like hydrochloric acid or diprotic acid like sulfuric acid. Now I need to find the molarity, so again I'm using my formula, moles of solute per liter of solution. We'll now apply this to the phosphoric acid. I just found the number of moles. I go back to my original statement of my equation. It required 14 milliliters to do this neutralization reaction. So actually this solution is quite a bit more dilute. It was only 0.0857 molar phosphoric acid. So these problems, these titration problems, are really solution stoichiometry problems. You have to keep in mind when you're dealing with mixtures, you have to use the molarity, and as all stoichiometry problems, you go back to your balanced chemical equation.